Okay, so what is my screen sharing working? It says it's paused.
Yeah, it works.
Let me just try again. It does this sometimes. There we go. Okay, well, thanks very much for the invitation to speak. Since this is, I understand this is meant to be a colloquium and a more general audience, I've tried to prepare a talk that starts with some generalities, but then towards the end, I'll get into more technical subjects, which are the things that we're excited about these days. As I'm sure all of you know, classical gravity, at least, is a geometric theory. The usual formulation, general relativity, relates the curvature of space-time to the presence of matter. And we think of, in that formulation, we think of the basic degrees of freedom as described by a space-time metric. And the primary property of this theory is its mathematical consistency. And what I mean by that, of course, is that everything's formulated in terms of tensorial quantities, and it's mathematically well-defined in the sense that it applies to arbitrary geometries and coordinate systems, etc. And that property in physics, we think of that as corresponding to the presence of a symmetry, which is diffeomorphisms. And this is a local symmetry, so gravity is often thought of from this point of view as a sort of gauge theory, but where the gauge symmetry is extremely large. It corresponds to all the diffeomorphisms of the space-time manifold. And the symmetry, of course, acts on everything in the theory. It acts on the components of the metric as well as components of any matter fields that you might include in the description. On the other hand, in traditional quantum field theories, gravity is not taken to be dynamical. It's instead defined on some fixed geometry. And we think about that, I mean, it's still a mathematically consistent theory, but because we're fixing the geometry, diffeomorphisms are not really symmetry because they would change the geometry that the field theory is defined on. And so there are conservation laws that come from certain diffeomorphisms that preserve the geometry. Usually this is Minkowski space-time in ordinary quantum field theories, and the conservation laws are things like conservation of energy and momentum, for example. What I'm going to focus on in this talk is the phenomenon of edge modes, as I said, first in sort of generality, and then in the specific case of gravity. And so what I mean by edge modes here is it's not necessarily anything terribly precise, but I'm just referring to the fact that in many theories, there are localized degrees of freedom within some larger system. So a simple example that occurs in many quantum systems is that you may find that there are wave functions, certain wave functions that are localized on some codimension K defect or interface or boundary. And for example, this is something that is extremely important in topological materials. It's sort of the basic physics in those cases. So that's a simple characterization of edge modes. As I said, they occur in a wide variety of systems. And on the other hand, we're often interested in dualities between physics in different dimensions. And there's sort of two classic examples of this. One occurs in Chern-Simons gauge theories, which in condensed matter physics describe the low energy regime of, for example, quantum Hall droplets. And one finds in those theories that there is equivalent dynamics on spatial boundaries which are described by Weston with conformal field theories. And I say here equivalent dynamics. What I should have said really is that the dynamics in Chern-Simons gauge theories really takes place on boundaries. And for that reason, or that's one of the reasons that we think of those theories as topological. This is a sort of topological duality, if you like. The other classic example is gauge gravity or ADS-CFT dualities. At least in certain limits, in this case, there's an equivalence between bulk dynamics. For example, you might just have semi-classical gravity and a quantum field theory on the conformal boundary of an asymptotically ADS spacetime. And we say that this duality is an example of a holographic duality, distinct from the topological duality in the sense that there really are bulk degrees of freedom, but that physics is conjectured to be equivalent to the physics of the corresponding dual quantum field theory. So in the latter case, this holographic principle is believed to be a fundamental property of gravity, or in general diffeomorphism invariant theories. And that's one of the reasons why it's of so much interest these days. So let me point out one important property. One sort of observable in quantum field theories that many of us have been studying in the last 2 decades, and that is quantum entanglement. So there are a lot of observables that one can carry over from quantum information theory to quantum field theories. The simplest example of this is entanglement entropy. And the only reason that I'm mentioning it here is that observables like entanglement entropy often inform about properties of boundaries or interfaces. So one of the earliest examples of detailed computations of entanglement entropy is now over 15 years old, where we studied entanglement in Chern-Simons gauge theories. And as I said, it tells us something about the boundary or interface or dual conformal field theory, because those observables in fact end up being expressed in terms of, in that case, WZW observables. And so this is often thought of as having deep physical significance, and the most elaborate claim along these lines is that that many people make is that in ADS-CFT, the bulk spacetime can be seen. It's believed, well, it's conjectured at least that the bulk within the field theory, within the CFT, you can sort of see, or the bulk spacetime emerges because of some quantum entanglement properties of the field theory. So let me expand a little bit about the significance of boundaries or interfaces in this regard. The sort of classic thing that people think about when they try to apply quantum information to quantum field theories is sort of a special case where the Hilbert space of the theory factorizes. So you and basically in these theories there are degrees of freedom at each spatial point, if you like, or if you just focus on some large subregions of space, you might say that the Hilbert space factorizes into a product of Hilbert spaces, one which contains degrees of freedom on one subregion and the other on the complement. And the way that these studies proceed is that given a state of the full system, you can define a quantum reduced density matrix that I'm going to call rho A here, defined on one subregion, or on the Hilbert space of one subregion. by tracing over the Hilbert space of the complement subregion. And then once you have that density matrix, there are observables that you can compute, and the entanglement is the trace of rho log rho, is the standard formula. Now, the point I want to make here, well, one of the points I want to make here is that this measures something not about bulk properties of the field theory on the region A or its complement, but instead it's something about the interface between the subregions. And the basic reason for that is that if you had done this calculation of the entanglement entropy in the opposite order, so if I had first traced over A rather than A bar and computed the corresponding entropy, you would get the same answer. Under some conditions, which I won't bother with. Okay, so the picture that I drew here, the cartoon that I drew here was meant to be a region of space. The interface between the regions then is codimension 1 in space, and so from the space-time point of view, the entanglement interface is codimension 2. And the focus in this talk, this is the first reason that we might focus on codimension 2, but the focus, as you'll see, will largely be on codimension 2 embeddings in space-time. So in contrast, if you talked about thermodynamic quantities such as thermodynamic entropy, in ordinary systems, those are extensive in space, so they wouldn't scale as the size of an interface, but instead they would scale as the volume of the total system. And famously, gravity has been known for decades to be different. For example, in black hole thermodynamics, the thermodynamic entropy scales as the area of the event horizon. There's this famous Bekenstein-Hawking formula. And well, this was often taken as evidence for the holographic nature of gravity. Again, it's a feature that's controlled by codimension 2. The horizon is codimension 2 in space-time. And it's believed that this is one of the reasons that it's believed that entanglement may be behind black hole thermodynamics. And so it's often said that, indeed, it's often said that black hole entropy can be thought of as entanglement between regions inside and outside of a black hole. Now, there's a problem with this picture in both in gravity, and in fact it would be a problem in any gauge theory. And the problem is that in gauge theories, the basic premise, the factorization of the Hilbert space that I referred to, fails. And it's sort of simple to understand at least in the gauge theory case, because there are degrees of freedom which are not ultra-local. Okay, so you don't just have degrees of freedom at individual spatial points. For example, in Yang-Mills, you have Wilson loops. And if I try to divide the space into subregions, then certainly there are loops that can be assigned to one spatial region, but there are also loops that straddle the interface. And what you should take from that is that if I try to take a gauge theory defined on space and split it up into subregions, there will be degrees of freedom on the interface, on what was the interface between the regions. And one has to take account of those degrees of freedom. They're physical degrees of freedom. And so one of my motivations in the work that I'm going to describe was to understand how this actually works in the case of gravity. Okay, which is, as I said, is in a sense a gauge theory, but it's not Yang-Mills theory by any means. let me go back and
ask you a question about the last slide.
Oh yeah, sure, Gabriel.
Actually, I've been thinking about this. So I was wondering if you think this statement about black hole entropy being entanglement entropy is general, or it's only true for, say, non-extremal black holes, because I'm always very puzzled that in the extremal black hole case where there is some string theory computation of the entropy.
Yeah.
Oftentimes, I mean, the standard geometry of alpha black hole counts the states associated with some branes wrapping some internal geometry.
Right.
And it seems to very much involve that compact internal geometry rather than having sort of having the Penrose diagram of the eternal, say, like Schwarzschild black hole with two sides, where there's a natural notion of entanglement of the two sides that I think is popularized via ADS-CFT and R equals EPR. Here, I'm just very confused about whether this notion of entanglement entropy equals black hole entropy should be true, because the actual computation doesn't seem like entanglement.
Well, I don't. So the Strominger-Vafa calculations, as you say, refer to very special cases where you can identify the degrees of freedom that make up the thermal state of the black hole, and there's a counting of those degrees of freedom. Indeed, that's a very specialized case, and I don't think there's a reliable calculation outside of that scenario. So I am not advocating that should be true. It may very well be true, but I think we're far from establishing it directly.
I see. So there's such a qualitative difference between like the special extremal case and sort of what you expect from a more general kind of black hole. Is that the right sort of guess?
Well, I'm not sure in what sense they're actually different. Why the extremal? Well, okay, so the extremal case, of course, has special features. I'm not sure if that's ultimately an important distinction. What I'm trying to point to here is that this picture of just talking about entanglement between degrees of freedom inside and outside is surely problematic in some sense because of the non-factorization of the Hilbert space. Right? In all of these discussions, at the end of the day, you are assuming factorization. And I mentioned, for example, that we calculated entanglement entropy in Chern-Simons theory. That's a gauge theory. And so, in a sense, we pretended in those calculations that we had factorization. And then, which was of course not a valid assumption. But at the end of the day, it turns out that it doesn't matter. Now, that was a case where it was a topological field theory. And so although the degrees of freedom are not localized in the bulk, there really aren't any degrees of freedom in the bulk, which is sort of why the picture hangs together.
Right.
You might think of that as an analog of perhaps of the extremal black hole, that there's a calculation there that appears to make some sense, but as you say, it depends presumably on the extremality condition, the zero temperatureness. But as well, it depends on having a lot of supersymmetry and all of that.
I see.
But yeah, so I think the jury is out on the general situation. I think there are very strong reasons to doubt that you can just pretend to use factorization, and there are hints here and there, right? That's all I'm really pointing to.
I see.
Now, what I'm motivated by, as I'll describe, is to understand how you might do better, how you might actually describe the sort of quantum features of a space-time.
Mm-hmm.
Okay, so
thank you.
Is that good for now? Okay.
Yes, thank you.
So now I have to reset and remember where I was. Oh yeah, okay. So the some of the work that I will describe at the end of the talk is fairly technical. And since I don't want to lose anybody, I thought what I would do now is describe in pretty simple terms the basic structure of classical dynamics from a symplectic point of view, just so that we're all on the same page. And I'm gonna write equations here that would apply to some mechanical system, but I'll describe how, as we go along, I'll describe how this generalizes to the field theory case. So the basic sort of Lagrangian formulation of mechanics starts with a Lagrangian density. It's a differential form on a space that I'm calling M here, which is the uncurly version of M. That M is just the, will in the case of particle dynamics would just be the world line of the particle. And the Lagrangian, which is the component of this form, depends on the values of coordinate space variables, q's, and their time derivatives, their derivatives along that one-dimensional manifold M. And you can think about that collection of objects, q, q dot, etc., as coordinates or describing a point in the jet bundle over M. And I'll call that curly M, but that's just the, and I'll often refer to it as the field space of the theory. Okay, so so that's what ordinary mechanics is described in terms of. In relativistic field theories, Q becomes a field. It depends on a spatial point as well as time. And the variable t here, the space M, the t coordinatized the space M, that's replaced by space time. Okay, and the Lagrangian density is then a top form on space time. Okay, so the usual variational calculus that we all learn in as undergrads is just corresponds, if you like, to moving on the field space curly M, and the general structure of a variation of L, which in this language can be thought of as a sort of exterior derivative in the space of fields. You can always write it in two terms, one of which gives you the classical equations of motion. That's the first term that I've written here. And a second term always occurs, which is just a total derivative. Okay, so I've written it here in the one-dimensional case, where it's just d by dt, but in the field theory case, this could just be written as an exterior derivative. Okay, so a total derivative. And that total derivative tells you something about the symplectic structure of the theory. So if the classic thing is to define a conjugate momentum, which is just this dl by dq dot. And what appears here is p delta q, and we think about that as, well, we think about the delta q's as basis forms on the field space, and so p delta q is a one form on field space, and I'm going to give the name theta to that. So that's the so-called pre-symplectic one form. And importantly, the variation or the exterior derivative on field space of that symplectic one form gives you the so-called symplectic two form. I'm going to use the notation omega for that. In simple classical systems, omega is just delta p wedged delta q as a form. And there's an important property of integrability that's going to play a central role in the talk. And what we mean by integrability is that there would be an equivalence between vector fields on the field space and functions on the field space. And the idea is that given that omega is a two form on the space of fields, you can feed it vector fields, or you can contract with, you contract the two form with a vector field that will give you a one form. And if it turns out that that one form is exact, in other words, if it's delta of something, we identify that corresponding function. Okay, so I write that as h sub v because it's a function that depends on the choice of this vector field. Okay, so if this happens, we say that h sub v is a Hamiltonian, and v is the corresponding v is a Hamiltonian vector field. Okay, and the point is that the usual Poisson bracket then between two such functions, which I've written here, can be obtained by from the symplectic form by just feeding it the two corresponding Hamiltonian vector fields. Okay, so here's two different notations for the same thing. And although this is very simple, and I hope familiar in simple finite systems, the details of this is fairly complicated in field theories. And this property, so often we're going to be interested in the case where V generates some symmetry. So for example, it may generate a diffeomorphism. It may actually be a vector field on space-time as well, in addition to the fact that it's a vector field on the field space. It may be a vector field on space-time that generates a diffeomorphism, as an example. But in the case of field theories, this integrability property, the equivalence between such a vector field and a corresponding Hamiltonian, is at least in question. I mean, it's you know, there are some details that you have to settle in order for that to be true. Okay, and the general idea here is that if you can do that, then you have a description or a representation of the symmetry in question on the field space, on the phase space of the theory. You have a Poisson bracket between the, you know, between different Hamiltonians here. Okay, so that's basic stuff. Now, of course, in when you have symmetries present, there are basic theorems, Noether's theorems, which apply to this case, which apply to the case where you have symmetries. And there are, as I hope is well known, there are two Noether's theorems. The first of which applies to global continuous symmetries. Let me just refer to that generally as lambda. And there's a conserved current, which is a corank 1 form on spacetime. And given the symplectic 1 form, if I think about that as a function of the delta q's and the q's, the Noether current is just given by replacing delta q by the symmetry variation of q. Okay, and then if I give you a hypersurface in space-time, I can pull back that. Remember, if I'm in d dimensions, this is a d-1 form, so I can pull it back to a hypersurface and integrate it. Okay, and that integral is what we refer to as a charge. Now, in the case of a local symmetry, as opposed to the global symmetry assumed here, this current takes the current density takes a special form, and that is that it's the exterior derivative of a d-2 form on shell. Okay, so there's some extra cruft here, but that extra stuff vanishes on shell when you satisfy the equations of motion. Okay, so Q, as I said, Q lambda is a d-2 form. So given a codimension 2 surface in M, I'm going to refer to these as corners, just for brevity. So whenever I use the word corner, I'm referring to codimension 2. There's a corresponding charge, which is just obtained by taking that Q and pulling it back to the corner and integrating it. Okay, and so the concept of the Hamiltonian that I was referring to earlier is this quantity in that case. So there's a familiar example, of course, in electrodynamics. What I'm expressing here is just Gauss's law. If I'm in 4 space-time dimensions, then a codimension 2 spatial surface, for example, might be a 2-sphere. And the thing that I called H lambda then is just integrating the electric field over that surface. Okay, so what you can learn from this is the hallmark of gauge theories is that they have charges defined on corners or codimension 2 surfaces. And that's a deep property of gauge theories, which of course is well known, that that's governed by Noether's second theorem, and it's been appreciated for a long time. But one of the problems has always been this integrability issue in this context. Okay, let me also point out that in fact this this structure, that in the case of global symmetries you have a d-1 form current, and in local theories you have a d-2 form charge density. That actually that's a basic property of holographic systems. Here I've drawn a cartoon of a space-time. You can think about this as an ADS space, where thought of as a solid cylinder with a particular metric in the interior, and the boundary of the cylinder is the conformal boundary of ADS. And the point is that if I'm in the bulk, in holography, the bulk theory is gravity, which is a gauge theory. So the charges would be defined on a corner, as we just described, which might be the boundary of a hypersurface that I've drawn here. Now, on the other hand, on the boundary in the field theory, if you think about the field theory as living on the boundary, the corresponding symmetries are interpreted as global symmetries, and those would have support, as we just described, on a hypersurface in the boundary, which indeed coincides with this pink curve here. So that's a basic, as I'm saying, that's a basic property of holography, is that gauge symmetries and in the bulk are dual to global symmetries in the boundary, and that fits the structure of Noether's theorem. Okay, very good. So Noether charges, of course, symmetries in general are very robust features of quantum field theories, and certainly we expect that to be true of quantum gravity as well. And let me sort of point out a slightly radical idea, which comes as follows. In gauge theories, we often use a description of the theory that that is simple in the sense that it's described as a local causal unitary quantum field theory, but we know that that is a redundant description. Okay, just the fact that there are local symmetries means that all of the fields that you have in the theory do not create physical degrees of freedom, if you like. Okay, as I've emphasized, in gravity, the local symmetry is diffeomorphism invariance. And a basic question is, well, if I give you an arbitrary diffeomorphism, is there a corresponding Noether charge, or are some of them zero, some of them not zero, that sort of thing. Should we think of classical spacetimes, as we usually use in general relativity, as a sort of redundancy? Okay, so normally the way that we think about this in GR is that we don't worry, we think that the spacetime is a fundamental object, and what we do is we just gauge fix all of the extraneous diffeomorphisms. In other words, we go to specific coordinate systems, etc. Now, as I said, the Noether charges are very basic degrees of freedom in a gauge theory. And so I'm going to explore the idea that perhaps we should think about codimension 2 surfaces as building blocks of a quantum gravity theory, of a quantum theory that has diff invariance. Okay, so this is very distinct from just thinking about a classical spacetime and quantizing fluctuations of something on that geometry. What I'm trying to suggest here is that it may be more fundamental to think of a classical spacetime as a sort of saddle point approximation, if you like, to a quantum theory that's built on some features of what in that spacetime would look like corners. And what I'm going to do is I'm going to focus on symmetry to try to build up a picture like that. Okay, there's a further subtlety in diff invariant theories in Noether's theorem, and the problem is that the action, although the diffeomorphisms are a local symmetry, the action isn't actually invariant on the nose. It's invariant just up to a total derivative. And as a result of that, there's this has a simple effect. There's a modification of the Noether current. So the second theorem still applies. The thing that I'm calling JC here is still an exact form. It's still DQC, but J itself is modified by an extra term. Okay, so it doesn't just come from the symmetry variation of the symplectic form, but there's a correction term. And that correction term is the problem that has plagued this field forever. The problem is that this apparently interferes with the integrability property. Okay, this is well known, but it's analogous to what happens in a much simpler field theory. There's an analog of this in Chern-Simons theory, where famously Chern-Simons is, as I said before, is a topological theory. It's equivalent to stuff that on the boundary, and part of the reason that occurs is that the action of Chern-Simons isn't actually gauge invariant. It's gauge invariant only up to a total derivative. Okay, and so in Chern-Simons theories as well, there's an analogous modification of the corresponding Noether currents. Okay, so a question that we asked ourselves last year was, well, what actually are the Noether charges in a diff invariant theory? And of course, people have been discussing this for 50, 60 years. As I've described, we know that the charges are associated with corners, right? We have some d-2 form in space-time that we need to pull back to a corner. And it turns out that, so the approach that we took in this regard was not to specify a particular classical theory, but to just think about properties of arbitrary diffeomorphisms in the presence of a corner. Okay, so what we need to do is we need to describe an embedded corner. So you can do this in local coordinates. You can choose coordinates that I'm calling sigma here on the corner. Okay, and you can describe the corner as an embedded. To be simple here, I'm just going to refer to these things as embedded, but you could talk about immersions, etc., or quotients or whatever. But I'm just going to use the language of embeddings here. So you would just, if the coordinates y are coordinates, local coordinates on M, you can describe the embedding by giving functions ym of sigma. And I'm going to set things up by adapting coordinates to the corner. Okay, so roughly speaking, the u's are normal coordinates to the corner and the x's are tangential. In particular, there's sort of a trivial embedding, which is this red curve that I drew in the picture, where the embedded surface is just taken to be at u = 0. Okay, and then essentially the x coordinates in the space-time M are identified with the with the coordinates on the spatial corner, which we're called sigma. Okay, and then the idea is, well, we're going to be interested in not necessarily trivial embeddings, but in embeddings which are sort of close to or sort of a variation away from a trivial embedding. And so if I want to address diffeomorphisms, this coordinate system is sort of useful in the sense that I can locally expand the components of the vector fields that generate diffeomorphisms in powers of U. Okay, and what one finds, in retrospect, it's sort of obvious, is that if you think in terms of an expansion like this, there are only certain leading components in the expansion that actually can contribute to charges. When you pull back to the surface, almost everything will get killed. So a simple example of this is the Einstein-Hilbert theory that just, is the action behind the Einstein equations. G is the metric here, R is the scalar curvature. And if you do the analysis, one finds that the nether charge density corresponding to a diffeomorphism C is this particular form. Okay, so what I do is I contract the metric with the vector field C, that gives me a 1 form. I take its exterior derivative, that's a 2 form, and then I take the Hodge dual, that gives me a D-2 form. Okay, so that's the result of a calculation. And then, if I use this sort of adapted coordinate system and evaluate the charges, what one finds is that most charges, as I said, are 0. For most diffeomorphisms, the charges are 0. But there is a closed subalgebra of diff M, which now is referred to as the extended corner symmetry. It's extended because it includes some what are in the lingo are called super translations. And it's this subalgebra which potentially gives rise to non-zero charges. Okay, so the picture here is that if I just gave you a bulk classical space-time, you would say that the diffeomorphism charges, because they generate local symmetries, would evaluate to 0 on physical states. Here, what I'm doing is I'm giving you a particular corner, a particular codimension 2 surface, and in a sense, the presence of that surface makes some of the local symmetries physical. In other words, they become sort of global charges, and they can be non-zero. Okay, so for example, the mass and other charges associated with black holes, for example, can be thought of in this way. Okay, and so in any case, certainly, the fact that we have a global symmetry here is certainly relevant. You would expect that the representation theory of that global symmetry is relevant to a quantum theory. Okay, now this group, let me just emphasize that this product that I've written here is the semi-direct product. Okay, so this means, actually I'll show you the details here. This means that the thing on the left acts on the generators to its right. So the diff S is just arbitrary changes of coordinates on the corner S, and the other components of the group here can be thought of as linear transformations of the 2 normal directions. It's 2 normal directions because I'm in codimension 2. Okay, and the algebra that I'm referring to here just comes from the Leigh bracket of vector fields on M, but the vector fields are restricted in such a way that the algebra closes. And when you do the computation, you find precisely the structure that corresponds to this semi-direct product.
Rob, can I ask you a question about this using the word corner here? Because when you allow for this super translation, so you're allowing for this that move the
absolutely.
So I'm a little confused. So like in the ADS-CFT case, the boundary is like codimension 1 in the sense that like
Right.
is time-like. But oftentimes when I see discussions of this corner symmetry, they're referring to like a causal diamond, so that the boundary is like no.
Well, you might think of just, you know, a constant time slice of the boundary. That's codimension 2. That's a corner in the bulk, right? So, but
sorry, what
I'm not at the moment. I'm not applying it to any specific situation. I mean, you could think about this, for example, sort of the general case is you could think of the corner as the boundary of some spatial subregion.
I see. But
Okay, so it might be, there are sort of special, that's sort of the generic case. And what it turns out that this symmetry or a very large subgroup of it is relevant to such that we call that a finite distance corner. It's just sort of a generic codimension 2 surface. There are special cases that I'll tell you about later, such as asymptotic, you know, celestial spheres in asymptotically flat geometries are corners from the same perspective, but they're associated with not the full symmetry. There's a reduction of the symmetry. Points along the horizon of a black hole are also corners, and they're associated with a subalgebra of this algebra as well.
I see. So in the case of ADS-CFT, you will also say that this algebra will contain the boundary. So for example, in ADS-3, would you say that this should contain the Virasoro algebra in some sense, or that's the kind of thing I'm trying to understand?
I see. Well, okay, so there are two complications here. So one is diff-S is a very large group still, right? Of course. But what you're asking is how does like an asymptotic affine symmetry arise from this point of view? And it's consistent with this, but there are details that go into the asymptotic limit that I'm suppressing here, but one can fit that.
So this contains everything. So this,
in principle, it contains everything. Yeah.
Okay.
Yeah.
Thank you.
And I'm probably going to run out of time, but you know, at the end, I'm going to give a very precise mathematical picture, or I'm going to try to, about how that comes about.
Okay. Thank you.
So let me try to get to the point. Okay, so let me refer. Okay, so the algebra that we just, this extended corner symmetry, let's just call that A, and suppose we have, so that's a Leigh algebra. And suppose I refer to an element of that as mu, and for this group, that mu is given as, in terms of three things. One is a diff S element, a vector field on S, an element of GL2, and a translation vector in a two-dimensional vector. Okay, and we would like to regard the corresponding Q associated with that element as a representation on the space of fields. Okay, so it turns out that in order to, so we thought about these charges, and then we thought, well, you know, the standard way to understand what the Leigh algebra actually is on the space of fields is to take a charge and vary it with respect to another element of the algebra. And as Gabriel just emphasized, there's a complication here because of the A's in particular here. These are translations of the surface. So in fact, we're not talking about just diffeomorphisms that preserve a surface. Okay, this also includes translations of the surface. Okay, so you know, so if you think about some sort of reference corner in red here, we have things that sort of move it locally away. Okay, and that's a crucial part of the algebra. And what we eventually realized is that from that point of view, if you want to vary a charge, then you have to pay attention to the embedding. In particular, when you vary the charge, normally what you would do is you would say, well, I move the variation inside the integral and apply it to the charge density. But the diffeomorphisms also change the embedding, right? They actually move the surface. And so the way that we think about that is that you should vary the embedding itself. Okay, and when you take that into account, you can take that into account systematically, and you just find that you get sort of the expected result, that the variation of the charge is just given by the charge of the Lie algebra bracket of the two elements of A. Okay, in other words, you actually, by varying the embedding, you get a representation of the full algebra on the field space, or you would get such a representation. Okay, so this ties back to the notion of edge modes, because it implies that you can't just think about the degrees of freedom here as the components of the metric that went into determining what the charge density was, but you have to supplement by degrees of freedom that have support on the corner that in fact describe the embedding. So if you like, the edge modes describe the embedding. And in a paper late last year, we realized that in fact you can formulate all of this directly in what's called the covariant phase space formalism by introducing an object, which I'm going to call chi here. It's the underscore means that it's a vector field in space-time, and it's a variation on field space. It's a one form in field space. And that's the basic object that you need to include, that you need to extend the theory by in order to describe these edge degrees of freedom that correspond to the embedding of the surface. And so let me just say a couple of words about this. So one of the structural properties is that the variation delta is thought of as an exterior derivative on the space of fields, and so it should be nilpotent. And if you follow through, if you impose that property on the extension here, you find that delta chi is not a closed form, but it's given by this formula here, and where the bracket is the Lie bracket. And this is a formula that, to those of you that know about BRST, this implies that chi is a sort of vertical form, or it's a diffeomorphism ghost, if you like. Okay, so again, these are degrees of freedom that otherwise would have been pure gauge, but in the presence of a codimension 2, of a specific codimension 2 surface, become physical. Okay, and the remarkable thing that we find is that if you include these new degrees of freedom into the theory, into the phase space theory, you find that there's a simple modification, there's a simple corresponding extension of the symplectic form, such that all of the charges, including the supertranslations, are integrable. Okay, and so since I'm so short on time, I'm not gonna dwell on the details, but I'll flash some formulas about how the idea is that you extend the symplectic form to include a simple term that involves this new field chi. And what's going on when you do that is, remember I wrote this formula where there was this problematic extra term that came because, the Lagrangian of diff-invariant theories is invariant only up to total derivatives. What's happening is that if you include this chi field, this term is in fact pulled in to the extended theta. Okay, so the formula for dq eta just becomes a contraction of an extended theta that involves this chi. And because of that fact, it turns out that there is no problem with integrability. Okay, now this is a little bit puzzling because, as I said, this has been a problem forever in gravitational theories. Normally the way that people do things is that they don't even think about some embedding or some extension of the phase space, and they just find that because of this extra term, the charges aren't integrable. And so what they do is they devise some elaborate conditions, boundary conditions and such, in order to identify some integrable part of the charge. Okay, so the claim now is that if you formulate things taking into account these edge mode degrees of freedom, in fact, there is no such waffling needed. Okay, so I basically said everything here already. The integrability, remember, implies that there's a direct correspondence between a Hamiltonian vector field and the field space. Now I'm talking about the field space extended by the edge modes and a Hamiltonian function on the extended phase space. Okay, and because the charges are all integrable, you get a Poisson bracket. So in fact, the variation of the charges that I referred to previously, which was sort of expressed in a general way, now is literally just the Poisson bracket on this phase space. Okay. Okay, so as we've referred to a couple of times in questions, you can think about this in various contexts. You can think about cases where particular corners have special significance. So, for example, along black hole horizons or along asymptotic null hypersurface, et cetera, et cetera. And we're sort of now studying the differences in these different cases. I've mentioned Chern-Simons theories many times in the talk, and it turns out that in that case there's a corresponding extension of the phase space also associated with gauge transformation. Chern-Simons, because it's topological, the action doesn't depend on a metric, and so it's a diff invariant theory. But the diff invariance as well as the gauge invariance is true only up to total derivatives. Okay, so in Chern-Simons, there's similar extensions of the phase space associated both with gauge and diffeomorphisms. Okay, so here's a simple example. Maybe I'll just, well, I don't know how much time do I have? A few minutes or?
Just a few minutes, yeah.
Okay. So here's a simple example. This is just a Schwarzschild black hole in 3D. What one finds is that you can express the charges that this black hole supports in this extended corner symmetry analysis. Okay, so you can look this up in the literature. Here I've translated it into my language. What this says is that there's no GL2 generator turned on, but there is a in this case S is one-dimensional, so it's just a diffeomorphism of a circle, say. Okay, so that's a diff S, and here the CV is a translation. It's a translation along the horizon, whereas the normal translation is set to 0. Okay, so this defines a subalgebra of the full extended corner symmetry. So this is just to indicate that one can describe situations like this in terms of the extended corner symmetry by using adapted coordinates close to the horizon in this case. And typically one finds not the full extended corner symmetry realized, but a representation of a subalgebra. Okay, let me skip that. I was going to refer to celestial stuff, but let me just finish up by saying a few words about something that we're writing up right now, which is to try to get an understanding of the representation theory of the extended corner symmetry by studying the orbit method. Okay, so applied to the Lie algebra of this full symmetry. Okay, the idea would be that, so if I call the Lie algebra little g, and its dual is G dual, then the charges can be expressed as integrals over S, involving the pairing of an element of the algebra and its dual. Okay, and now the Poisson bracket in this picture is just sort of a, it's intrinsic to the surface S. I'm just studying a symmetry now. I don't need the classical space-time, which S was embedded in. I can just think about things intrinsically. And the Poisson bracket of these things is just given by the add star action. Okay, so you get the known result immediately. And the interesting thing here is that it's instructive to look at the coadjoint orbits of the two last factors here. So you can think about this, what I'm referring to here, as sort of point by point on the space S, if you like. And the coadjoint orbits of this group, this semi-direct product, in fact, is very tractable. This is a 6-dimensional group, 4 + 2. And the general theory gives rise to it. So this is a 6-dimensional group, and the generic orbit, in fact, is 6-dimensional. Okay, and the general theory gives rise to, well, what happens is that the orbits are symplectic manifolds, and there's a standard KKS symplectic form associated with that. Okay, so if you study a generic orbit here, the KKS symplectic form turns out to be non-degenerate. And it turns out that it splits up into 2 pieces. One that involves the trace. So I'm using local coordinates on the dual, which you can think of as generators of GL2 and generators of the R2. And because I have GL2 here, that J has a trace, and the symplectic form splits off a term that involves the trace. It's canonically conjugate to something that I've called C3 here, and everything else that I haven't written here is about the SL2 and the R2, the SL2 subgroup of GL2 and the R2. So this is a rank 2, a 2-dimensional subspace of this 6-dimensional space, and there's a 4-dimensional space here. Now, the sort of remarkable thing is that there are various symplectic reductions that you can do here. So one thing that you could do is you could take a quotient by the trace of J. So I just mean I'm going to think about delta trace J as 0. And so what that does in the symplectic form is it just gets rid of the first term, right? It just leaves the ... dots. And what's left is, in fact, the KKS symplectic form of a generic orbit of SL2 semi-direct R2. This is a 5-dimensional group. A generic orbit is 4-dimensional. It has to be even dimensional because it's symplectic. And what happens is that C3 becomes a Casimir of this SL2. It's this particular cubic Casimir. So this is not a Casimir of GL2. It's actually a dynamical variable, but when you reduce to this subspace, it becomes a Casimir. So there are orbits that are labeled by values of C3, if you like. This is a sort of an invariant description of what I referred to as a generic finite distance corner. There are other quotients, and it appears that if you quotient in a certain way by the SL2, and in other words, if you sort of throw away, you quotient by elements of the SL2, the resulting orbit is 2-dimensional, and it's the generic orbit of this group. And this is a group which is referred to as BMSW. It's the symmetry group associated with an asymptotic corner. So for example, if I'm in an asymptotically flat space-time, this is the symmetry at infinity that, for example, features in celestial holography and all of that. Okay, it's the symmetry that preserves some set of fall-off conditions in the bulk. And similarly, corners along a black hole horizon correspond to a closely related but slightly different quotient by SL2. Okay, so I'm really out of time, so let me finish up. So what I think is sort of exciting here is that this group theory analysis that I just described appears to give rise to a characterization of corners that we know are important in gravity, but it's an analysis that is done without explicit reference to an underlying spacetime. It's just the representation theory of this extended corner symmetry. Now, given, and so, you know, the nice thing about this, I think, the exciting thing is that this is presumably quantizable. There's presumably a quantum theory that one can introduce here, and there are so the game here is to study the representation theory of the extended corner symmetry and or the relevant symplectic reductions that I just referred to, and that, you know, there will be representation theory that is that corresponds to any particular examples of the symplectic reductions. And I think that from this point of view, a classical spacetime can be viewed as a sort of emergent geometry that describes some collection of corners and the representations of the corresponding symmetry. Okay, so I'll stop there and take any other questions you may have.